All right. Okay. So Newton's third law is about action and reaction. So Newton discovered that for every action that you make, there's always a reaction to it. So for example, when you're pushing against the table pushes you back. If you push the wall, technically the wall pushes you back with like normal force. So we actually do have a name for that kind of forces. So for example, the first example would be you have gravity, and then if you apply a force on the table pushes you back with the same amount of force, just going in different direction. And we call that one a normal force. Now it turns out that it works for everything else too. So this is Newton's third law. For every action, so for every action force, there is a equal. So there is an equal. Now equal in what? Equal in magnitude. That means same size. But opposite. So equal but opposite. Opposite in what? Opposite in direction. So equal in magnitude but opposite in direction. So opposite in direction, reaction force. So for every action force, there is an opposite, equal but opposite reaction force. Okay, so action, reaction force. Now, so that means forces always kind of, come in pairs. So you have action, you apply a force in one direction, then the object that you're pushing or pulling will apply a force in the other direction to try to counterbalance you. So we call those forces action and reaction pairs. So for example, when you apply a force on the table with Fg, then the table responds by applying a force on you called Fn. Now, but you can also extend that to a lot of other situations. For example, when you hit a baseball, I'm sure you have played some kind of sport where you need to use a thing to hit a ball. For example, baseball, badminton, or table tennis or tennis itself. When you hit the ball or golf, you will feel sometimes the ball actually pushes you back. To be honest, sometimes it hurts a lot. For example, the first time I played tennis, I didn't realize that it was actually going to be that demanding on your hand. When you hit the tennis ball that's going at you at really fast speed, you actually feel quite painful on your racket. Like even though your racket is hitting the ball, but you feel like there's a huge force trying to bounce your racket back. You have to force your hand forward, and it is quite painful. So it turns out that, you are hitting the ball, but the ball also hits you back. So for example, if you are trying to hit the baseball with a bat, now this is my attempt to draw a bat right here. Okay, so this is a bat. Some people, yesterday's class, say this looks like a fish. I'm very sad. This is a baseball bat, okay? Baseball bat. Now, so when you use your baseball bat and you swing it and it hits like a baseball, this is the baseball. So what happened at that moment? Okay, so at that moment, two things happen. So first of all, you hit the ball. So there will be a pi force, from the bat hitting the ball, which is like a pi force right here. So the bat hits the ball, and then so the bat hits the ball, right? So the baseball bat hits the ball. And then what happened? What happened is the baseball bat is actually hit by the ball too. So the ball hits the bat in the opposite direction. So the force is equal but opposite. Equal but opposite, like this. Okay. So the baseball actually hits you back with like a normal force, I guess, in this case. So the baseball bat, the ball, also hits the bat. Okay, so the bat hits the ball hits it back at the same time. The force is equal but opposite. Okay, so it's always equal and opposite. Now, next example, third law. So another example you can talk about in Newton's third law is running or walking. Walking or running. Now, it doesn't even have to be sprinter starting running. It can just be a normal person starting to walk. Okay. Now, I want you to get into this thought exercise. Okay, if you want to walk forward, which way do you actually push? You push backward. You realize that? When you try to walk forward, you push backward. If you try to swim forward, you push the water backward. You don't push the water forward. If you push the water forward, you actually go backward. You see, because what happens when you try to walk is you actually apply a force backward. Everyone does that. Like when you try to walk, you take a step backward. You kind of push backward. And then what happens is the ground will push you forward. Okay, you apply a force backward, the ground push you forward. What is the force that the ground push you forward with? Surprisingly, it's actually friction. It's actually friction. So it's the friction between the bottom of your shoes and the ground that pushes you forward. So therefore, that's the reason why it's so difficult to walk on ice. Because friction is very small, so you don't get a good grip, and it's very difficult to move forward. Okay, so you push the ground pushes you back, right? Those are the force pair. How about a little fish swimming? Same idea. We kind of talked about that already. So this is a little fish swimming. So when a little fish swims, they swing their tails and they apply a force backwards. So the fish pushes the water, then the water pushes the fish forward. And that's why the fish can go forward. So the fish pushes the water pushes the fish goes forward. Okay, so fish pushes water, and then at the same time, the water pushes the fish in the opposite direction with the same amount of force. The fish. Okay, so fish push water, water push the fish. Right, perfect. Now, even though the force is the same though, but sometimes, as I was explaining earlier, who gets more damage depends on the mass of the object. Yeah, 1,000 Newton force on your body is like taking a strong punch. 1,000 Newton force on a dinosaur or on an elephant is nothing. They won't even move an inch. But 1,000 Newton force, the same amount of force on a mosquito, whoa, they fly off really fast. So it depends on how massive the object is when they take the force. So for example, when you imagine a bug, which is small, hitting the windshield of a semi-trailer, which is like a truck, big car, right? So what force pairs occur? So you have your gigantic like truck, and then you have a little bug like this, little tiny bug, right? Like this is a little bug right there. Okay, so the car go forward and hits the bug, and then it gets smashed to, it get hit and land on the screen like this. So at that moment, what happened? Well, first of all, the truck hits the bug with a applied force, and then the bug hits the truck with an applied force, going in exactly the opposite direction, except they also have the equal in magnitude. So equal in magnitude, but negative in, opposite in direction. So the force pairs are this. So the truck hits the semi-trailer, or the truck hits the bug, and then at the same time, the bug will hit the truck with the same force. Now, most important thing, Newton's third law says, with the same force in opposite direction. Now, but how come the bug is the one that's flying off and the truck is not flying off on the other side? Well, that has to do with mass. Okay, that has to do with mass. So which force is greater? Same. The force is exactly the same, Newton's third law, in opposite direction. But which object will have greater acceleration? Now, that's what I was saying before. Acceleration depends on your mass too. So again, if the force is 1,000 Newton, pushing a dinosaur doesn't move it much. Pushing a cat moves it a lot. So which object will accelerate faster? The object with the smaller mass is easier to push. So which object accelerates faster? The bug. Okay, the bug will accelerate faster because it's the mass of the bug is much smaller than the mass of the truck. Okay, and the acceleration depends on mass and forces. Remember, Newton's second law is F net equals to ma. So the acceleration depends on mass too. The more massive an object is, the smaller the acceleration, keeping the same force. So the more massive something is, the smaller the acceleration. It has to be like that. Okay, so now the final, okay, so another, just 3 more example, which is just a drawing. So for example, when you fire a gun, like a water gun or BB gun or actual firearm, actually, the body of the gun. Now, so this is like a gun with the bullet inside. So when you fire a gun, what happens is that the gunpowder inside the bullet explode. It turns from a solid form to a gas form that expands rapidly in volume. Now, the gas has nowhere to go, so it pushes the only thing that can be pushed, which is the bullet. So the bullet goes forward, right? So the gun pushes the bullet forward with like an applied force from the explosive gas. But at the same time, the bullet, the gas also pushed the gun backward with the same applied force. So what happened is the bullets move forward, but at the same time, the guns move backward. That's called recoil. So the more powerful your bullets are, the more your gun will recoil back at you. So if you are holding that, gun, for example, you will have to hold it really firmly. Otherwise, the gun will just fly off. And sometimes people aim like this with the gun directly in front of their face. The first time they try the shooting range and they fire, and then they get a low speed after. Because what happened is you fire, the bullet go forward, the gun go backward, up, and then you hit your nose. So that's why they always teach you, okay, please hold the object with two arms, right? The gun with two arms, because the recoil are going to be surprising. The more powerful the bullets are, the better or the stronger the recoils will be, because the faster you push the bullet, the stronger the bullet pushes you back. Okay, there is no going around this. Cannon, it's the same thing, right? When the army have like cannons, they have to prepare for the cannon to move backward. So yes, the cannonball move forward, but your entire cannon actually go backward. So you do not stay behind the cannon after you fire. You stay beside the cannon. If you actually watch like footage of the old war when people actually use cannon back then, they don't stand behind the cannon. If you stand behind the cannon, there's going to be like a 2,000 kilogram cannon rushing and crushing you after the cannonball go forward. You stand beside it, you light the fire, you light the fuse, and then you go like beside it, and then you cover your ears. You will see the bullet go forward, the cannonball go forward, and the cannon itself move backward like a meter or so. So if you stand directly beside it, you are going to get hurt, seriously hurt. Okay, so there's always an action and reaction. You cannot expect something to go forward without something going backward. Okay, so when you karate chop something, so karate chop, right? So why does the brick? So you apply a force on the brick, which is like an applied force. At the same time, the brick is trying to respond and apply a force on your hand, which is kind of like a normal force repelling. Now, the reason why you hurt, the brick doesn't hurt is, again, the pain receptor problem, right? The brick doesn't have any pain receptor. You hurt because however small amount of pain receptors you have on your hand is still flesh and bone. The brick is still inanimate object. Remember, Mr. Chang says, human versus inanimate objects always win, right? They don't hurt, you do. But you're able to break it, but it will also hurt yourself. Now, this idea from Isaac Newton was actually brilliant because he even predicted the creation of flying machine. Remember, Newton was born in the 18th century. They don't even have cars back then, let alone plane or rocket. They don't have them. They don't even have car. They have like horses carriage. Right? They have like horse cars, not like engine cars. But his idea was the fundamental building blocks of rocket engine. Now, people think, okay, so how can I make something fly? Now, Newton said, if you apply a force in one direction, that object will apply a force to you in the other direction. So what do? In order to make rocket, this is what we do. We get some gunpowder inside or, explosive inside, which is solid, and we ignite it. When we ignite it, it turns into a gas, right? Now, when it turns into a gas, it expands rapidly in volume and it wants to go somewhere. The front of the rocket, you seal it off so the gas cannot go there. And you make a hole in the bottom so that the gas have to go the other way. So that means, what is the rocket doing? It's actually just pushing a lot of gas backwards. Pushing a lot of gas backward. And what happened is the gas will then push your rocket forward. And that is how we have liftoff. So you just have to keep pushing gas backward. Your rocket will move forward. Okay, so you can say the rocket, right? So the rocket pushes the gas As long as you aim it in the direction that opposite to the direction you want to go, then the gas will push your rocket in that direction, which is the fundamental theory behind, engine. You just have to push gas the other way. Then your object will go one way. And this idea was thought of 100 and 200 years ago, before even electricity was a common thing. Pretty amazing. Okay, so that's that right here.